Okay, welcome students. I'm a little bit surprised by the high turnout today. And actually, usually people are very happy when there's a high turnout. I'm a bit disappointed because, well, we have ample space here, and even if you sit on the wings, I think it's pretty difficult to see the screen. On purpose, I set up this whole shebang to get a live stream and a recording working. So if you feel not comfortable in the room here, please go sit somewhere else and look at the live stream, or even later, at a later time, at the recording. Okay. What are we going to do today? As I said before, we always will start with an in-class quiz. So we will start today with a Kahoot in-class quiz. After that, I will do the theory of chapter 2 of the book. For those who have looked at Brightspace, they see that the lecture notes are now chapters from a book, the sequel to the Advanced Dynamics book, which you had in the second year. We're now going to broaden that by adding multibody dynamics, and as we go along, I'm busy forming these chapters. So it's work in progress. So on a week-to-week basis, you will get the various chapters of the book, and at the end, then you're sort of done. Yeah, I have no more announcements. Let's start Kahoot. But before we do that, let's see what were the instructions for the in-class quiz. Yeah. Okie doke. Now there's a lot of text, and most of the text you already read, of course. But I'm going to repeat a little bit. It's about participating. So wrong answers are 6 out of 10. Correct answers are 10 out of 10. Please discuss during the time when the question is open. That's the whole purpose. But of course you are right and your neighbor is wrong. So try to convince him or her. We have to enter a PIN number. And the most important thing is that you are able to enter your student ID without commas. If you are able to do that, you get credit. If you're not, bad luck. If you say afterwards, oh, I was Mickey Mouse, and please enter my grade because this is my student ID, forget it. I'm not going to do that. You have to be now correct, because then I get piles of emails with, oh, please, can you enter? No, I'm not going to do it. So enter now your student ID together with some nice nickname. I choose 4123455 Ariboy. That's clear, that's me. What else? The timing is 60 seconds or 90 seconds. Some questions you have to do a little calculation in your head or on paper. Those are the 90 seconds questions. And for the live stream, 10 seconds of delay. So 10 fingers, 10 seconds of delay. Be aware. If you say, oh, I pressed at the last minute. If you're on the live stream, sorry. You have to be 10 seconds in advance. Yeah, okay. Kahoot. See. Play. Oh. Looks good. Yeah, so please log in. We have to wait a little bit before everybody is connected. I expect a number of participants around 14 something. Oh, no. It's gonna be more. Oi, oi, oi. I have the power to kick people out. Yeah, well, I mean, it is stated, please don't use offensive names. I'm very powerful. Okay, it feels to me that we sort of, in an exponential way, found some saturation in the number of participants. So let's start the quiz. It's 5 questions, if I'm right. Well, I think the quiz also tells you. Yeah, 5 questions. Are you ready? This is about free body diagrams. I remember Heike was very strict on this. You can also put the live stream on, eh? Oh, yeah, okay. So there were 2 correct answers. Let's look at the. So apparently this was a correct answer, and this was wrong. Well, it's wrong because. Why is it wrong? We don't put D'Alembert forces in a free body diagram, right? This one was correct. I mean, yeah, you can choose forces along and perpendicular or in the xy. That's no. All the dimensions are there. Applied forces. This one is wrong because there is no torque here. Eh? There was no friction, no drag, nothing. Okay. Yeah. 68 people, please. Check the advanced dynamics. Karan, is he in the room? Good. The hero. Okay, rotation matrices. "90 seconds. Let me see, full screen? Yeah, that's better. Very good. Um, so what is it? Can I have some silence in the room, please? Yeah. So why is it this blue answer? Well, the sequence is, of course, you have to transform from this space fix to the body fix. So you have to go along this series of hinges. So the first transformation you have to do is, of course, according to this hinge, and then the second and then the third. So thinking you have to read backwards, Rn times Ra times Rb times Rc gets me into the body coordinate system. Very good. I'm impressed actually by the number of correct answers, because it's always you always I also always make a wrong order, like oh no it's the other way around, yeah, or the transpose, or okay. Karan, keep up the good work. Okay, a bit about mass moments of inertia. Mass at the distance squared, remember?
The masses are on either side, so it's m1 squared. Okay. Yeah, okay. And mass is 1. So that's 2 times r. So, or, mine is not there.
So if I look at the number of incorrect answers, that is exceeding the 50%, meaning that a lot of people have to brush up their mass moment of inertia chapter, right? For those who have to brush it up, actually, let's look at the thing. So it's mass times distance squared, and it's about an axis. So let's say, for instance, about the z-axis. It's about this mass, this mass, this mass, and this mass. That's where the rotation is about. So before you do any calculation, the first step you do is, of course, what is the biggest and what is the smallest, which axis? Now, if you look at the figure, then about the x-axis and the y-axis have both this contribution of the large z masses. So those are big. So the smallest one is actually, of course, the z-axis, because there the distance is short and it's distance squared. So we have to pick an answer where among the z-axis is the smallest. That's the first. So let's look at the answers. Well, this will fall off. This is incorrect. This could be right and this could be right. And then the second thing is, well, we just have to calculate it. Huh? Mass times distance squared. Well, the mass was 1, that was easy. And here I have 1 mass and the distance is 2, so that's 4. The same here, plus 4 is 8, plus 1 is 9, and then we come to 10. So, okie doke. Next one. Karan, super good. Tensile force in the rope. Okay, this is the easy one, right? Well, apparently not. Some people mix up velocity with angular velocity, right? So the red answer is angular velocity when you think W is is linear velocity, and of course the correct answer is this. Yeah, okay. Super. Then the equation of motion in X. So this is about a mass spring mass system. Yeah. Yeah, the majority is right, very democratic. There is some misconception with the blue, and that's, yeah. So the blue answer is, oh yeah, that's always the equation for a vibration. Mass times acceleration plus k times x is 0. That's not the case. I mean, we have loading here, gravity, so we have gravity loading, but also the unstretched length of the spring always gives a force. Yeah. Okay. Good work. Rudan in the room. Sit. The next time you go, sit there. Who knows? Frank? Yeah, but Frank is my helper. Good work, Frank. Okay. Now, it's sort of nice to give feedback. I would appreciate if you give feedback. And if you think it sucks, just say so. No problem. Well, I will not hold it against you. I cannot even hold it against you because it is anonymous. Yep. Yeah. Okay. I've saved everything. That finishes the in-class quiz, but maybe I grab this one. What was it? So we leave the in-class quiz now, and we go back to. Oh yeah, I have to get this one back. Okay. Okay, there we go. Come on. Let me check if this is still running. Yeah, that's okay. We go here. And we make this size. It's good. Yeah. Okay, so now we continue with a little bit more content. The topic of today being free body diagrams, which was part of the quiz, Newton-Euler equations and constraints. Again, everything I scribble here is saved. You can download it again from the website. Everything I write down here is in the lecture notes, which are on Brightspace. So if you make notes, only do it for your own memory. Do not copy the stuff here. Okay, Newton-Euler equations. Well, to be more specific, I would like to say these are the Newton-Euler equations, and what do they describe? Well, they are actually the equations of motion. This last part is actually pretty important because they help us with setting up the equations of motion from which we then can solve the motion. Now, we're not going to look at general bodies. We only do it now for a rigid body, and moreover, only for now, and that's after the break, we will explore space, but for now, we're only going to work in the two-dimensional world. And that is, well, first of all, it's pretty scary out there in space. It's really, because rotations, I mean, they're hard to grab. And in the two-dimensional world, I can illustrate most of the methods we will develop here, and then you can apply them directly also to the three-dimensional world. Okay, so let's dissect Newton-Euler equations of motion. Well, we're interested in motion. We want to have equations for that, and then we have two words, Newton and Euler. What is the Newton part? Well, everybody is familiar. We say the sum of the forces equals the mass times, you could say acceleration, but if you read Newton, who has read Newton? Yeah, great, come on. If you read Newton, then he actually says this, that if you apply a force to a system, then in some ratio, some fixed ratio, the velocity will change. And that was his whole concept. So if you apply no force, then every object will remain its velocity. Will not change. So of course, we think then, oh yeah, velocity is also a time derivative of position, dx dt, and then we can substitute that into the equation here, and then we say, yeah, the sum of the forces is the mass times the acceleration. And of course, that is how we usually know the law. But it's very good to always keep in mind, oh yeah, forces, they change the velocity. Yeah? Now, for what type of objects did Newton derive these equations? Of course, I know the answer. It's not a rhetorical question. I want answers from you.
Rigid bodies.
Rigid bodies. Well, is that really point mass? Yes, I was seeking for the word point mass. And what point masses was he thinking of? Apples? He had a grocery, or what was going on? Yeah, that's true too. I will get back to that in a second. One of the answers was also the moon and the sun. But let's stick to the apples first. So he was not a grocery. He didn't have a grocery, right? He was not having an apple yard, or was not making cider. Inside. What was he doing? In those days, there were these plagues, and he was living in the city of London, and in London you had the Black Plague, and smart people knew you have to run for that, because we don't know exactly what it is. It will make you sick, and you will probably die. So the only way is to run. And so he ran to the country, but then, what to do? I mean, if you are there in the countryside, there's nothing much to do. You have some books, but not your whole library, and that is where the whole story emerged, where he was sitting under an apple tree, and then suddenly thought that, well, it is true that he was bored out there, and that he was thinking about, not about apples, but about what makes the heavenly spheres move, and the heavenly spheres being the sun, the earth, the moon, and all the other objects I observe in the sky. And there was already a long quest, of course, going back to Copernicus and Kepler and so on. But still, the basic idea is why do they move as they move? I now have this idea with forces and mass, and so he developed this whole theory just on the basis not of apples, so that's not true, but it was the sun and the earth, and also the moon, here, the moon, and they all go in circles around each other. So they move like this, and they move like that around it, and then the big question is why do they move like they do? And so there must be forces between them. And then he came up with that idea about this mutual attraction, so that the earth is pulling on the sun, and the sun is pulling on the earth. And those two forces are equal and opposite. Action in magnitude equals reaction, but it works in the opposite direction. That's one of his laws, which he also developed. And of course, he also developed a law that how big are these forces? He said, well, the forces between those two objects is some constant, which you just have to determine. And then if this is the mass of the sun and this is the mass of the earth, then it goes something like this. And then if this is the distance r between the objects, then it's r squared. And it's not r to the power 3 or r to the power 2.7849. No way. It's r squared. And I always find that magical. And so the whole idea of gravity, do we know what gravity is? No way. We have no idea what it is. We know that two masses, in our model, in our physics model, two masses attract each other. And we call it gravity. But the working principle, we have no idea. There are volumes of books written about gravity, and we still have no idea what it is. But it works, right? No, it works. Look, gravity works. And how? We don't know. Anyway, he formulated the laws, and the things, moved according to these laws. So the laws fitted perfectly well on reality. Are they always true, these laws? Newtonian laws?
No.
No. When are
Relativity theory.
yeah. So when the velocity is almost zero, they are okay. For very slow motion, like flying from here to America, slow motion, it's okay. But the moment you go in the vicinity, if your velocity goes into the vicinity of the speed of light, then things change. And then there is some correction factor, and that's again square root. It's not to the power 0.3859 or so. No, it's really the square root out of 1 minus, and then it's v over c squared. And you already see that, well, c being a very large number, c is in the order of 10 to the power, help, 9? 8? Thank you. Oh yeah, 300. Yeah. 2 over 3. No, yeah, 8. Okay. And that's fast, right? 3 times 10 to the power 8. 300 and then 10 to the power 6. So that's really fast. So this only comes into play when you really move very fast. And that is what we're trying to do in the cyclotron and all these other nice research instruments. Okay. So back to Earth. Forces is mass times change in velocity, works pretty well. That's the first part. And now the second part, there's a second name, and that is Euler. So what about Euler? Well, where does Euler come into play?
Rotation.
Yeah, exactly. And when does a point mass rotate? We don't know. I have no clue. A point mass is an object without any dimensions, right? It's a point. So, yeah, points cannot rotate. The moment we talk about rigid bodies, then suddenly we have rotation. So rigid bodies is this sum of all these point masses. And then we have this concept of center of mass. And then we draw a line on the body. And then we say, with respect to some horizontal, this line will change in orientation. And that's what we call rotation. So they have an orientation, bodies, rigid bodies. So only when we talk about rigid bodies. So, and the story behind that is also pretty funny. Euler was a smart guy. Actually, I should have called this whole set of lectures the Euler lectures. Because I bet you that every week when we treat a subject, suddenly, beep, the name of Euler will pop up with another Euler discovery, or another Euler law, or Euler parameters, or Euler angles, or it's Euler all the way. So actually the whole course should be called the Euler course, right? Well, no, because Euler did far more than mechanics. He did also other fields. So the Euler course would be wrong, actually. The Euler mechanics course or something like that. But even I'm not able to touch all the subjects. So let's go back to Euler. Euler, a smart guy. How did he get into rigid bodies? I mean, it's not that you wake up in the morning and think, oh, I'm going to write down the equations for rigid bodies. Yes. Does anybody know? Well, actually, he was contracted by one of the Bernoulli brothers. Now, the Bernoulli brothers, it was a big family, with a lot of scientists within the Bernoulli family, and they mainly had to do with fluid dynamics and so on. We know the Bernoulli law that fluid moving has what we call the dynamic pressure. That's all the energy, the kinetic energy which is in it. And the dynamic pressure is equal to 1/2 times the specific mass times the velocity squared. And that's something the Bernoulli discovered. They were busy with hydraulics and so on. Now, the Bernoulli brothers also wanted to know about ship motions. And the only laws they had were the laws by Newton. Now, and the Newton laws, they talk about the point mass. Now, if you are interested in the motion of a ship and you say, well, let's assume the ship is a point mass, then, well, yeah, okay, you know how much force you have to apply to start it moving and how much force to lift it, maybe. But all the motions like the rolling motion of a ship or the pitching, no, it's different. The heave, no, this is heave. Roll, well, let's say call it pitch and yaw, but in maritime world they have again other names. But so the rolling, the pitching, and the yawing, that's something which has to do with orientation, with the body. So the Bernoulli brothers understood that they couldn't solve that with their Newtonian mechanics. So they just called this guy Euler. Hey, Euler, can you help us? And then Euler said, yeah, sure, I can. It's not so hard. It's just a collection of point masses rigidly attached. And so Euler developed the whole mechanics for these rigid bodies. And what is the law he came? Well, in this case, we stick to the two-dimensional world, right? So we have some origin, we have some xy coordinate system, and then the law goes like this. We have the sum of the torques about the center of mass is the mass moment of inertia about the center of mass times the angular acceleration. So that is Euler's law for a rigid body in 2D. Now the ICM at the CM is the sum of all the individual masses times the distance of every mass with respect to that CM squared. That's this definition of this mass moment of inertia. Moment, of inertia. And this is, of course, the angular acceleration, and this is just the sum of all the applied torques. So now we have a nice law, and we can talk about change in orientation and so on. In the quiz, we saw an example of such a mass moment of inertia, and I always like to think in simple terms, like, oh yeah, you have mass at a distance. So if you have this dumbbell here, and let's say this distance is r and the mass is m, this thing, then we know immediately that the mass moment of inertia, this is the cm, because you model this finally as saying, oh yeah, this is some rigid body with a mass and a mass moment of inertia at the cm. Well, the mass at the cm is of course 2m, mass at the cm, sorry, cm. The mass at the cm is of course 2m, and the mass moment of inertia at the center of mass is of course I can't hear it, sorry. R squared. I like R squared, yes, times.
Because it should be times m over 2m.
Remember this, it's the sum of the mass times the distance squared. So for this mass times it's mr squared plus mr squared, so in total making 2mr squared, right? So 2mr squared. And if you have a more complex the mass distribution, you just have to do an integral of, or sum it up, or cut it into parts and add everything up, whatever you like. Okay. So now we have our laws of motion for a rigid body, and we're going to derive the equations of motion for a general 2D multi-body dynamic system. That's not good. System. Now, we can do that in theory by just nicely deriving all kinds of equations with a sum force and a mass I, but we can also do it by example. And I think that's actually the best way to start learning a new topic, is just say, okay, let's take some simple example of a multi-body dynamic system and see if we can derive equations of motion in a sort of a general way. The example I like to do is what I call a simple manipulator. And it's of course a human-based one, because, yeah, I see everything out of my own perspective. If I look at the world, I interpret it from out of my own eyes, and I see myself within the world, and I am the center of everything, right? That's life. So I know a very simple human-based simulator, and that is this thing, right? Face a bit strange. Yeah. So we're going to focus on this thing. It's a nice manipulator. It's very nice. You can reach positions in space with your hand. You're not, well, I have an extra object here, which should not be there, but I'm not going to cut it off. I'm not going to model the hand. So it's just, the hand is rigidly attached to the underarm. So as you already see, you're not able to put the hand in any position and any orientation. So that's already a deficit of this manipulator. If you want to do more, you need to add some more degrees of freedom probably. But for now, let's keep it simple. A 1 degree of freedom system, that's too simple because that's just the Newton-Euler equations. So let's just add one, 2 degrees of freedom. So that is the manipulator, and yeah, you can say it's a 2D manipulator, but you can also say it's a double pendulum. So then we draw it in a little bit different way. We say, oh yeah, it's something like this, and then we call it double pendulum. And to stress that it's really about rigid objects. Oh, I first had the hand here. Then we make even a nicer drawing to show that no, it's really about rigid objects. So it's one object like this, and attached to that is hinged another object like this, and here it's hinged to the ground. It's always good to put a coordinate system with it. There's an origin, we call this A, X, Y, this is point B, and the end effector is C maybe. We can enumerate the bodies, so this is body 1, and this is body 2. They have a length, of course. This is L1, and here they have a length, that's L2. There is gravity. Now, usually gravity is down like this, but yeah, then everything goes down, and down is negative, and then negative y, and so I like to fiddle a little bit with gravity, and I can do that. So I just rotate the gravity. I'll rotate on, sorry. Rotate on, come on. So I put the gravity like this, if it's okay with you. So let's put gravity. So gravity is horizontal. It's a bit strange, but it makes that the thing just moves like this in our, if we plot it and so on. And otherwise it will start like this, and then we'll do everything is minus y. I don't like that. Well, anyway, the position of the bodies we call x1, y1, and phi1. Now for phi1 we have to be specific, so really the angle with respect to the horizontal. And for the second body also the same, this is then phi2, and again this position is x2, y2, phi2, 3 coordinates. Of course we have mass here, m2, and mass moment of inertia, and the same here, m1 and I1. And that sort of, I think, completes the whole problem. And what we like to know, so given also the gravity force, we want to know actually what is the x1 of t, the y1 of t, the phi1 of t, x2 of t, y2, and phi2 of t. So, so given forces, and then the question is, what is the motion? Dubbele punt. Hè? Ja. No, that's a good question. Thank you. So the question in the audience is, the coordinates, are they absolute coordinates of the bodies, or are they relative coordinates within a body frame? No, these are absolute coordinates, absolute inertial frame, and we call it usually n, so this is n coordinates. And there's a slight difference between frames and coordinate systems. That's the origin, but Heike knows all about it. If you want to know, just ask her. Okay, so the x1, y1 is just, that's the position of the center of mass of body 1, and x2, y2 is, that's the position in the inertial world of body 2. And if we want to know the motion, yeah, we actually want to know how do, what are they as function of time, given some initial conditions, some initial position, or some initial velocities. That is our quest. And to solve that, of course, we need equations of motion. Or some people are maybe very smart and say, oh yeah, I know that's the sine hyperbolicus of this or that. I have no clue. Okay, after the break we continue.